Good morning, friends and dear students. I feel immense pleasure to be here for my course Engineering Thermodynamics. Today I am in the definition and the terminology of the module 5th, that is the heat transfer and the compressor. In this lecture I will be discussing the definition and the terminology of 5th module, which is related to the heat transfer, conduction, convection, radiation, also the compression and all. So what is the heat? Define the heat transfer. A thermodynamic analysis is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to another. The science that deals with the determination of the rates of such energy transfer is the heat transfer. The transfer of energy as heat is always from the higher temperature medium to the lower temperature one. Heat transfer stops when the two mediums reach to the same temperature, that is called the equilibrium. Define the conduction. Conduction is the transfer of energy from the more energetic particle of a substance to an adjacent less energetic one as a result of the interaction between the particles. This happens normally take place in the solid, liquid and the gases. In the gases and the liquid, the conduction is due to the collision and the diffusion of the molecules during their random motion. In solids, it is due to the combination of the vibration of the molecules in a lattice and the energy transport by the free electron. A cold cane drink in a warm room, for example, eventually warms up to a room temperature as a result of heat transfer from the room to the drink through the aluminum can by the combustion. So if you take a cold drink bottle of aluminum foil, inside you have taken out from the fridge and you keep outside. Outside the temperature is high, inside the bottle the temperature is very low. So from the liquid to the aluminum foil, it is the conduction, and from aluminum it will go to the air. So here conduction and the convection both are applicable. Rate of heat conduction depends on the geometry of the medium, its thickness of the material of the medium, temperature difference across the medium. So these are the 4 points which conduction is dependent. Define rate of heat conduction. Experiment has shown that the rate of heat transfer, that is Q dot, through the wall is doubled when the temperature difference delta T across the wall or the area A normal to the direction of the heat is doubled, but is half when the wall thickness L is doubled. So it is inversely proportional to the thickness and also directly proportional to the temperature difference and the area perpendicular to the surface. Thus we conclude that the rate of heat conduction through a plane layer is proportional to the temperature difference across the layer and the heat transfer area, but it is inversely proportional to the thickness of the layer. So rate of heat conduction is directly proportional to the area and the temperature, and it is inversely proportional to the thickness. So Q of conduction is equal to Ka T1 minus T2 by delta X or minus Ka delta T by delta X. K is the thermal conductivity, which is measure of the ability of the material to conduct heat. In the limiting case, if delta X extend to 0, the equation above reduces to the differential form. We can write as a Q conduction is equal to minus dt by dx, which is called the Fourier's law of heat conduction. Here dt by dx is the temperature gradient, which is the slope of the temperature curve on a Tx diagram, the rate of change of T with respect to the X at the location X. Area A is always normal to the surface. Minus sign ensures that the heat transfer is in the positive X direction. it is positive quantity. So in this, you can see in this diagram that, so define the convection. Convection is the mode of energy transfer between a solid surface and the adjacent liquid or the gas that is in motion, and it involves the combined effect of conduction and the fluid motion. The faster the fluid motion, the greater the convection heat transfer. In the absence of any bulk fluid motion, heat transfer between a solid surface and the adjacent fluid is by the pure conduction. The presence of the bulk motion of the fluid enhances the heat transfer between the solid surface and the fluid, but it also complicates the determination of the heat transfer rate. So here this you can see that the velocity, as it is increasing, at the high velocity you have the less temperature, and at the surface you have the high temperature. So temperature variation of the air is shown, and here the velocity variation of the air is shown in this diagram. Defines Newton's law of cooling. Heat transfer process that involves change of phase of a fluid are also considered to be convection due to the fluid motion induced during the process, such as the rise of the vapor bubble during boiling or the fall of the liquid droplets during the condensation. Despite the complexity of the convection, the rate of convection heat transfer is observed to be proportional to the temperature difference and is conveniently expressed by Newton's law of cooling as, so this is the Newton's law of cooling. Q dot convection is equal to HAS Ts minus T infinity, where H is the AS is a surface area, Ts is a temperature of the surface, and T infinity is a temperature of the surrounding. H is the convective heat transfer and its unit is watt per meter square degree centigrade. AS is the surface area, Ts is the surface temperature, T infinity is the temperature of the fluid sufficiently far from the surface. Now, convection heat transfer coefficient H. The convection heat transfer coefficient H is not a property of the fluid. It is an experimentally determined parameter whose value depends on all the variables influencing the convection, such as the surface geometry, the nature of the fluid motion, and properties of the fluid, and the bulk fluid velocity. Typical values of H are given in the table. If you can see here that for the free convection and the forced convection, free convection of the gases 2 to 25, free convection of the liquid is 10 to 1000, forced convection of the gases, it is somewhere 10 times, and boiling, and here also it is 10 to 1000 to 50 to 20,000, so nearly 20 times it is higher. Boiling and the condensation, it is very high. So this H value will depend upon the free convection or the forced convection, and also boiling and the condensation. So these things we have to remember. So now introduction to thermal radiation. This I can say here that define thermal radiation. Thermodynamic radiation, or the radiation, is the energy emitted by the matter in the form of electromagnetic waves or photons as a result of the changes in the electronic configuration of the atoms or the molecules. Unlike conduction and the convection, the transfer of heat by radiation does not require the presence of an intervening medium. In fact, heat transfer by radiation is fastest at the speed of the light. It suffers no attenuation in a vacuum. This is how the energy of the sun reaches the earth. In heat transfer studies, we are interested in thermal radiation, which is the form of radiation emitted by the body because of their temperature. It differs from other forms of electromagnetic radiation such as X-ray, gamma ray, microwaves, radio waves, and the television waves that are not related to the temperature. So It is a temperature-related electromagnetic wave. We cannot compare with radar waves or some communication wave or navigation wave. So, for microwave and other things. All bodies at a temperature above absolute zero emit thermal radiation. So, every body has to emit the thermal radiation. So, Stephen Boltzmann constant, the maximum rate of radiation that can be emitted from a surface at a thermodynamic temperature Ts in Kelvin on the Rankine is given by the Stephen Boltzmann's law. So it says that Q dot emit maximum is equal to sigma As Ts to the power 4, where sigma is 5.670108 watt per meter square Kelvin to the power 4. This value is constant. For any numerical, we have to use this value. The idealized surface that emit radiation at this maximum rate is called the black body. So if any body is emitting the heat in this rate is called the black body and is called the black body, and the radiation is called the black body radiation. The radiation emitted by the real surface is less than the radiation emitted by the black body at the same temperature and is expressed. So the real body will not express the same temperature, but it will be Q dot emit is equal to epsilon sigma As Ts to the power 4. So this epsilon will give less than 1, and epsilon is 1 for the black body. So this epsilon is called the emissivity of the surface, and this value fall between 0 to 1. Here this you can see that if the temperature here is Ts 400, Q emitted is equal to epsilon Ts to the power 4 for a unit area, you will get 1452 watt per meter square radiation will be there. Now define absorptivity. Another important radiation property of a surface is its absorptivity alpha, which is the fraction of the radiation energy incident on a surface that is absorbed by the surface. Like emissivity, it is its value also between 0 and 1. A black body absorbs the entire radiation incidence on it. That is, a black body is a perfect absorber, that is alpha is equal to 0, and it is a perfect emitter also. In general, both emissivity and the absorptivity alpha of a surface depend on the temperature and the wavelength of the radiation. Next, we have the Kirchhoff's law. Kirchhoff's law of radiation states that emissivity epsilon and the absorptivity alpha of a surface at a given temperature and the wavelengths are equal. So, the value of the emissivity epsilon and the value of the absorptivity alpha will be equal for a given temperature. In many practical applications, the surface temperature and the temperature of the source of the incidence radiation are of the same order of the magnitude, and the average absorptivity of a surface is taken to be equal to the average emissivity. The rate at which a surface absorbs radiation is determined from the figure here. So, this you can see here that it is a absorbed and it is a reflected. So, Q dot absorbed is equal to alpha into Q dot incident. So, it is a Q dot incident here, and reflected how much? It is Q reflected is equal to 1 minus alpha into Q incident. So, where Q incident is the rate at which radiation is incident on the surface, and alpha is the absorptivity of the surface. For opaque or non-transparent surfaces, the portion of the incident radiation not absorbed by the surface is reflected back. Now we will define the rate of heat radiation. So we will see here that when a surface of emissivity and the surface area As at a thermodynamic temperature Ts is completely enclosed by a much larger or black surface at thermodynamic temperature, T surrounding separates by a gas such as air that does not intervene with radiation, the net rate of radiation heat transfer between these two surfaces given by the figure here. This you can see here. This is the surface here, this one. And it will radiate, and it is incidents are coming, it will reflect also. So it is emitted also and it will radiate also. So Q dot radiation is equal to epsilon sigma As Ts to the power 4 minus T surrounding to the power 4. So it is the surrounding, this is the surrounding and this is the surface Ts. So Ts to the power 4 minus T surrounding to the power 4, and this will be in watt. The emissivity and the surface area of the surrounding surface do not have any effect on the net radiation heat transfer. So this emissivity and the surface area of the surrounding surface do not have any effect on the net radiation of heat transfer. Now what is the heat exchanger? Heat exchangers are the devices that facilitate the exchange of heat between two fluids that are at different temperatures while keeping them from mixing with each other. So these heat exchangers are the devices which used to transfer the heat very fast. You see all the engines. Outside of the engine you will see some baffles are there, very small fins are there, and there are a number of fins arranged in a very systematic way. Same way for the air conditioner and all, you can see a very big, when water is flowing with a tower, those all are the heat exchangers. So heat exchangers are the devices that facilitate the exchange of heat between two fluids that are at different temperatures while keeping them from mixing with each other. They will not mix each other. Application from heating and air conditioning system in a household to chemical processing and power production in the large plant. Heat exchangers differ from the mixing chamber in that they do not allow the fluid to mix. In a heat exchanger, we don't allow heat to mix. Heat transfer in a heat exchanger usually involves convection in each fluid and conduction through the wall separating the fluid. So here convection and the conduction is the main heat methods by which heat transfer is taking place. In the analysis of heat exchanger, it is convenient to work with an overall heat transfer coefficient U that accounts for the contribution of all these effects on heat transfer. The rate of heat transfer between the two fluids at a location in a heat exchanger depend on the magnitude of the temperature difference at that location, which varies along the heat exchanger. Define the regenerative heat exchanger. Another type of heat exchanger that involves the alternate passage of the hot and the cold fluid streams through the same flow area is the regenerative heat exchanger. The static type of regenerative heat exchanger is basically a porous mass that has a large heat storage capacity such as ceramic wires mesh. Hot and cold fluid flow through this porous mass alternatively. Heat is transferred from the hot fluid to the matrix of the regenerator during the flow of the hot fluid, and from the matrix to the cold fluid during the flow of the cold fluid. Thus, the matrix serves as a temporary heat storage medium. So, I have done with definition and the terminology, and next few classes I will take the discussion on the question bank on all the modules. For this, I have taken some references. They are from P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's 4th edition, 2008. Eunice Senegal, Michael A. Bors, Thermodynamics and Engineering Approach, Tata McGraw-Hill's, and this NPTEL from IIT Kanpur. Any questions, you are welcome to ask to my email, or you can comments on this video. And please like and subscribe this channel. Till then, thank you. See you for the question bank session.
Like, share and subscribe. Hit the bell icon for more updates.